Hello everyone, today let's take a look at QP151 where we have the values 1 through 6 in a bowl, right? So we draw them without replacement, noting the order in which we selected them, and then we multiply the first two, the next two values together, and then the last two values together, and then we add the three products, and then we find the probability that the sum is odd. So for example, one example run through this problem, maybe we get a 1 on our first draw, and then we get a 2, and then maybe we get a 4, and then maybe we get a 5, and then we get a 3, and then we get a 6. And then what we do is multiply the first two numbers that we got together. So in this case, we'd get 2, multiply these two together. In this case, we get 20, and we multiply these two together. In this case, we get 18, right? Then we add them all up, and we're going to get 40, which is an even number. So in this case, we'd get an even product. We want to find the probability that this sum right here is odd. First thing to notice is basically how even and odd numbers work, right? If I have my odd numbers here, I have 1, 3, and 5 that I could possibly draw. And then for my even numbers, I have 2, 4, and 6. Now, when we multiply an even number times an even number, we get an even number, right? Because the definition of an even number is that it is a multiple of 2, right? So if 2 is one of the numbers in the prime factorization here, it's also going to be in over here, which makes this one an even number, right? Now, when we multiply an even number times an odd number, well, this one's going to have 2 in its prime factorization because it is even, so will the product with any other number, right? So this is also going to be even. But now, when we multiply an odd number times an odd number, the definition of an odd number is that it doesn't have 2 in its prime factorization. So in that case, we're going to get another odd number. So in this case, we had an even times an odd, so we got an even number. In this case, we did as well, and same with this one. All three were even times odd, so we got 3 different even numbers, right? Now, if I sum up 3 even numbers, I'm going to get another even number because, again, all of these are going to have a factor of 2 in them, so we can pull basically this 2 out, and then we're going to have basically 3 numbers. I'll call them x, y, and z, and then this is going to be equal to some value. I'll call it like m, right? And then m will be divisible by 2. So that makes the sum of 3 even numbers an even number as well, right? So when I sum up 2 even numbers, I get another even number. When I sum up 2 odd numbers, I also get another even number because the definition of an odd number is that it's basically just 2 times k minus 1, or k is just some integer, right? So it's going to be 1 less than some multiple of 2, right? 1 less than some even number. So when I sum up 2 odd numbers, I'm basically summing up 2k plus 1 and 2m minus 1, right? And then this is going to simplify to basically 2m plus 2k minus 2, and you can factor a 2 out of this right here, which makes this over here an even number. Now, when I add an odd number to an even number, I'm going to get an odd number. Why? Because this is some multiple of some integer, right? 2m, and this is 1 minus some multiple of some integer, right? 2k minus 1. So when we add these up, we're going to be able to factor a 2 out of m plus k, but we're still going to have this negative 1 out here, right? Which makes this entire thing odd. So those are just some basic obvious number things that you have to know in order to be able to solve this question. So now that we know that, basically if I have an odd times an odd times an even, an odd times an even, like I do in this case, and I sum them up, well, I get an even number. And the only other way that I could group these, not paying attention to order, would be O, O, E, E, and then basically O, E. Where I have my 2 odd numbers here, we know that's going to be even. My 2 even numbers here, when I multiply them, that's going to be even. And then odd times an even will give me an odd. And then when I sum these 3 up, well, an even plus an even will give me an even. And then I'm summing an even with an odd, which will give me an odd. So in this case, I get an odd. And in this case, when I sum these 3 up, I get an even. And in this case, I'm not talking about order at all. I'm just saying basically I have 2 even groups, right? 2 groups such that their multiplications are even. And then I have 1 odd group, right? 2 even, 1 odd. And for this one, I just mean basically 3 even, right? Those are our only 2 options. There's no other way that we could have it, right? It's either 3 OEs or 1 EE, 1 OO, and 1 EO. Now, the probability that the sum is odd. We know the total number of ways, first of all, to choose all of these 6 elements or have them come out is just going to be 6 factorial, right? We have 6 options for the first thing that we draw. We have 5 for the next thing that we draw. We have 4 for the third, and etc., all the way down to the 6th thing that we draw, for which we will have 1 option, right? So 6 factorial total ways to draw these things from the bowl. But now the number of ways such that when we multiply the first 2, the middle 2, and the last 2, and then sum them up such that that is odd, well, let's calculate that. And now, like we talked about before, the only way to get odd is if we basically have 2 evens grouped together, we have our 2 odds grouped together, and we have an even and an odd group together. So to count this, we essentially have 3 distinct groups, right? My even group, my odd group, and basically my even odd group. So let's say we choose our even group first, right? I have 3 even numbers, and they are they're not 1, they're 2, 4, and 6. I need to choose 2 of them to be in my 2 even group, right? So I have 3 choose 2 ways to choose 2 of my even numbers to be in this group of 2 even numbers. Once I've chosen 2 of them, let's say it was 2 and 4, right? Then I have 2 and 4. Well, then I have 2 ways to permute them within this group, right? So times 2. That's because in my even group, I could either have 2, 4, or I could have 4, 2, right? There's two options, right? That's why we multiply by 2, and that's the same for every single group of 2 from these 3 even numbers. Now, same thing for odds, right? I have 3 options. They're going to be 1, 3, or 5, right? So I have 3 choose 2 ways to choose 2 of these odds to be in the group of 2. And then once I've chosen those, I have 2 ways to arrange them. So if I choose 1 and 3, then I have 1 and 3, or I could have 3 and 1. And now finally, when I choose my even odd group last, let's say I chose 1, 3, 2, and 4 beforehand, well then I only have one way to choose this even odd group, right? Because I only have 2 numbers remaining that satisfy that, right? 5 and 6 in this case. So I have one way to do that, but then within this group, my 5 and my 6, I can permute those in 2 factorial ways. So again, I have to multiply this number here by 2, and now I multiply all 3 of these together. So 3 choose 2 times 2 times 3 choose 2 times 2 times 1 times 2, but that just satisfies this arrangement right here, where basically our 2 evens come in our first 2 positions, right? 1 and 2. So I still have to account for the fact that I could get an odd sum of these 3 if I had my odds come first, right? Same if I had my even and odd come first, right? It doesn't matter the arrangement of these 3. When I sum them up, I'm still going to get an odd number. So therefore, we have to multiply by the total number of ways to arrange these groups relative to each other, right? So once we have these, the number of ways to actually choose the elements for our groups, the number of ways to arrange them are just going to be 3 factorial, because we have 3 items, we can permute them in any of 3 factorial ways. Now we've accounted for everything, so now we can basically just do this out. 3 choose 2 times 2 is just going to be 3 factorial. 3 choose 2 times 2, again, is going to be 3 factorial. Then we're multiplying that by 2, and then we can just multiply the whole thing by 3 factorial, so times 3 factorial in here. Now 3 factorial is equal to 6, so we basically have 6 cubed times 2. 6 cubed is 216, so times 2 we're going to get 432. So basically 432 ways such that we get an odd sum when we multiply our first 2, our middle 2, and our first 2 elements together and then sum them up, right? So that's going to be the final answer, right? 432, and then the probability is going to be divided by the total number of ways that we could pull these 6 things out of the hat. So 6 factorial, well, 5 factorial is 120, so 6 factorial is 720, so 432 out of 720. That in lowest terms is equal to 3/5, so that's going to be the final answer. Now, just to verify, we could also calculate the probability of evenness and see that if the probability of even and the probability of odd sum up to 1 to know that we did it right. So let's calculate the probability of us basically getting an even term when we sum up these 3 multiples of our 2 elements, right? So the only way to get basically 3 even is going to be when we have an even and an odd group together, an even and an odd group together, and an even and an odd group together, right? So 3 groups of an even and an odd, like we did up here. Now we can go through in much the same process, right? We're choosing, first of all, one of our elements to be in this first group of odd and even, right? So we need an odd and an even element. There are 3 odd and there are 3 even that we could choose from. So 3 times 3 different options for this first group. So that, again, more formally, that was just essentially 3 choose 1 times 3 choose 1. And now once we've chosen our 2 elements, right? 1 odd and 1 even, well, we could have basically 2 and 5, let's say. Well, then we have 2 ways to permute this within this group, right? Because we could have 2, 5, or we could have 5, 2. So 3 times 3 times 2. Now for the second odd even group, right, I'm going to have already chosen one of my odd and one of my even, so I'm going to have 2 odd and 2 even remaining for that group. And then once I've chosen those, let's say it was basically, 3 and 6. Now we have 2 factorial ways to permute these, so we have to multiply this again by 2. And same vibes for my last group, right? I'm only going to have 1 odd and 1 even left at this point. So I have 1 way to choose my odd and 1 way to choose my even. So 1 times 1, 1 way to do that. And then once I've chosen those, I basically have 2 factorial ways to permute them. So 1 times 1 times 2. Now, do we have to account for all of the permutations of these? No, we do not. And that is because these are all basically the same type of group, right? They're all odd even types. Because once I've chosen my first odd even pair, right, I have all the combinations of possible odd even pairs to go in positions 1 and 2. So all the things I get over here are, again, just kind of going to be the leftovers of basically what I didn't choose to be in here, right? So if I chose 2 and 5, then I'm going to use all the leftovers from my finals. So then I might have my 3, 6 here, and then I might have basically my 1, 4 right here. But then in this number right here, I'll also have already counted my 3, 6, and I've also already counted my 2, 5 in the leftovers of that, right? All of this. And then I've also already counted basically my 1, 4 in all of the leftovers of that. So there's no need to account for the position of these groups when they are all the same, versus if you look back over here in our odd case, we had 3 distinct groups. That's because we were grouping an even and an odd and an odd, and an even and an even. So if over here I chose my even and my odd group first, so I'd have 3 times 3 times 2, same as over here, the total number of ways to choose an even and an odd number. number. Let's say I got 2 and 5. But now over here, I'm choosing two odds, right? So I'd have to choose 1 and 3. And this is not basically going to be included in all of the counts for basically the even and the odds, right? Because two odds is completely different than an even and an odd. So I just have to account for that fact by saying basically the odds can come before the even and the odds, versus in this case, it didn't have to be true because again, these were all basically the same type of group. They're all odd even pairs. So sorry if that was confusing, but basically back to the original question, the probability that they're even, we don't need to multiply by this extra factor of 3 factorial to account for the ordering. So we can just multiply all of these together, right? We're just going to have 3 times 3 times 2. Well, we have 4 2's right here, and we have a fifth one over here. So we're basically times 2 to the fifth. So we have 9 times 32 here, which is going to end up equaling 288. So we have a 288 out of 720 chance of getting an even sum, right? And then we can pretty clearly see that 288 plus 432 is going to sum up to 720, which is just like we would expect. Just like with all combinatorics questions, there are probably other ways that you could do to count this stuff, but I feel like this way is the easiest. So basically all this question boils down to is knowing how even and odd numbers work, right? How they sum and how they multiply. And then just knowing how to constructively count these groups effectively. And when you do all that, you get a final answer of basically 3/5. This is our final answer. The probability that this sum right here is odd when we take basically these two numbers, these two numbers, these two numbers, we multiply them, and then we sum them up.